My name is Himansh, and today we're going to find out the survival probability of a blind rat. Okay, so this question is based on the random walk model. So first question is that there is a blind cat and a blind rat on a square lattice. So the box length is of length L and the grid size is R. So the total cells can be given by L square by R square. There are two cases. At time t is equals to 0, the rat and cat are located at diagonally opposite corners, and the second case is that the rat and the cat are the center of the lattice. The second question is that the blind rat and the blind cat are on a sphere. Here also there are two cases. The first being that at time t is equals to 0, the rat and the cat are diametrically opposite to each other, and case 2 is that they start at the same point. Okay, so we'll be also looking at the answer to some questions such as how does the survival probability of rat vary with time and etc. So first we'll hop on to the first question and first answer. Part 1 is that the survival probability of a blind rat and a square rat. I have already told the initial conditions, so I'll just note down the boundary conditions of the problem. So the first boundary condition is that the cat and the rat reach at any of the four corners. If the cat and rat reach at any of the four corners, they will take a rest with probability 1/2 and move in a direction with 1/4 left from remaining 1/2. Both cat and the rat can move in any direction with equal probability, that is 1/4, because we know that there are four directions for the cat and the rat to move, and with all of them with equal probability, so the probability would be 1/4. The third boundary condition is that if for edges rest 1/4, moving 3/4 divided equally, giving 1/4 each direction. We need to find the survival probability. So first we'll find out the probability of rat being caught, and then we'll subtract it from 1 to find out the survival probability. Okay, so let us take the t to be the total number of steps which we take, which the rat and the cat take. Okay, so if we assume that x are the number of steps along the x direction, so the number of steps to the y direction would be t minus x. So let us assume that they meet at a coordinate n1 comma n2. The probability of them being at n1 comma n2 can be given by probability of them being at n1 into probability of n2, as x and y moments are independent of each other, so we can just multiply them together. So we can directly input the values into the formula, which we already know, that the probability of n1 will be the total number of steps in x direction, which is x c n1 into 1/4 raised to power the number of steps to the to the left, right, to x in x direction, and 1/4 into number of steps into the y direction. So we just put the values, and we can find out we have the expression of p probability of n1. Similarly, we can also find out the probability of n2, which is t minus x. We'll just replace x by t minus x, because we know that the number of steps in the direction along y-axis is t minus x. Now, as we have the individual probability, we just need to multiply with each other, and we can find out the total probability. Just put in the values and we have the probability. Here we know that the t is the total number of steps. Okay, so the probability of rat and cat being at n1 comma n2 after t steps can be equal to this expression. Okay, so here the problem is that x is a variable value, so we need to find the whole range. Okay, so we just take the limiting cases in which when x is minimum we have it as n1, and when y is minimum we have it as n2. We know that x plus y is t, that is the total number of steps, so x max would be t minus y min, which is equal to t minus n2. Okay, so the probability of random walk with rat and cat in this case of meeting at n1 comma n2 after t steps would be this whole expression which we have it. I just inputted the values in the formula, and we have this expression. Okay, so now we have two cases. Like the first case is when rat and cat start from opposite corners. Okay, so here n1 n2 varies from 0,0 to n1 comma n1, and from n to n, capital N to comma capital N. Okay, so we arbitrarily take a coordinate, so let it be n1 comma n2, Okay, so probability of meeting would be probability of the cat meeting at n1 comma n2, and then multiply the probability of rat meeting at n1 comma n2. Okay, so basically cat starts from 0 comma 0 to n1 comma n2, the rat starts from n comma n to n1 comma n2. Okay, we just input the values and we have the final expression like this. Okay, we just need to keep in mind that this part of the expression is the probability of the cat reaching at n1 comma n2, and this part of the expression is the probability of rat reaching at n1 comma n2. Okay, in the second part we have that the rat and the cat start at the center, okay, at t is equals to 0. So basically what we have is that the problem, as they start at the same point, that the displacement of both of them would be same. So these two quantities would actually be equal to each other. So here we have the square probability of n1 comma n2. Okay, so just input the values and we have it as the probability of meeting as this whole expression whole square. Now we know that we have already found out the probability of mating. Now we just need to find out the survival probability, which would be 1 minus the probability of mating. Okay, so just I subtracted the whole expression from 1 and get the required answer. So for the second part, we have that the cat and the rat are moving on the sphere in any direction, taking equal steps at a time. So, okay, so at any point on the sphere, I can represent by using two values. Okay, so I have two angles which are theta and alpha. Theta makes with z axis and the alpha is the angle of the point tangent with the x and y plane. Okay, so for a fixed theta I can draw a circle around the uh, sphere at some particular latitude and I get a ring. Basically I get a ring. So for that probability of alpha I can find out, which is can be easily found out by arc length divided by circumference. Okay, so just I inputted the values and I found out the, in order to find out the probability for theta, I just the probability of theta can be found out by area of the ring divided by surface area. I just inputted the value and cancelled out the common variables and I get sin theta d theta by 2. Okay, so as we know that both of these probabilities are individual of each other, so if I just multiply them together I can get the total required probability. As we did in the first question, instead of x and y I just have theta and alpha, so I just use the same concept and I just multiply these two quantities together to get the final probability. So as you have found out the total probability, I just need to find the like after displacement d, if the initial theta and alpha and theta were as like alpha and theta, so they'll change to alpha nu to comma theta nu. Okay, so I have taken two reference lines a comma b. A is the longitudinal angle with x and y, xy plane is alpha, and b is the latitude angle with z axis is theta. Okay, so just I found the d theta, which is d cos b by r. Then but the thing is that after displacement the new theta would be theta minus d cos b by r. Similarly, I can find out d alpha, which can be d sin b by r sin theta, and alpha nu would be alpha plus d sin b by upon r sin theta. The important thing to note here is that I can easily take minus or positive. It depends on my choice, because the thing is that the particle, the animal can move in any of the two directions. Okay, it can be either minus or plus. It doesn't actually matter as long as we're going to integrate it. So like it doesn't matter anyway, the answer would be same. Okay, so if we just for sake of convenience we assume small displacement, so the rat and cat will cover the complete surface of the sphere. Okay, so the probability density function, which I denoted by omega theta alpha comma alpha d theta d alpha, which we need to calculate. Okay, so we have the probability theta comma alpha. Okay, we just input the values and the final probability of the meeting can be easily found out by if we integrate the probability density function over over all possible values of alpha and theta. Okay, we know that the alpha varies from 0 to 2 pi and theta varies from 0 to pi. Okay, so you just put in the limits and integrate the whole function and we get the probability of meeting as this function. Now as we have the probability of meeting, to find out this probability of survival we just need the probability of meeting. We just need to subtract the probability of meeting from 1 and we get our final answer. Okay, so this I have just completed the two questions. Now I'll move on to the part where to answer few specific questions. The first question is that how does the survival probability of rat vary with time, which can be easily found, like this is actually true that in both the cases the survival probability decreases with increase in time. So we can easily find out that the probability of survival is inversely proportional to time raised to power some constant k. Okay, so for a very large time we know that eventually no matter what, how less the probability is or how big the grid is, eventually the cat will meet up with the rat and eat it. So the probability of survival will tend to zero for a very large time. Okay, so the second question is that does the survival probability depend on length of the square and radius of the sphere? Okay, so which can be easily found out. Like first of all, yes, the probability depends on length L and radius of the sphere respectively of both the equation. Okay, so here when length is very much greater than 1, see, so the probability of survival remains 1 for a large amount of time. So subsequently the probability of survival is is proportional to 1 minus 1 by L square, which we can find out by the equation we have just calculated above. Okay, and similarly, probability of in the second part, B part of the same question, the probability of survival is proportional to 1 minus 1 by r raised to power 4. Here, this can be derived from the equation which we have derived above in the second part, in the second part of the second question. Okay. Now on to the third question, which is that can you determine the limiting value of survival probability when the step length is infinitesimally small and the number of steps is sufficiently large? Yeah, obviously I can easily find out the probability. Okay, so which is like first I'll find out the probability of meeting and then I'll subtract it from 1. So like for infinite number of steps, it's 1 by L square and I just subtracted from 1, so the probability of survival will be 1 minus 1 by L raised to power 4. Similarly for sphere, in which it would be 1 minus 1 by 4 pi r square whole squared, which is 1 minus 1 by 16 pi square r square. Both of these formulas can be easily found out if we tend the number of steps to infinity and make the length infinitesimally small. Okay, now like for the fourth question, I'll just solve these problems computationally, which actually means I'll just show you the graph, like how does the probability varies with time. Okay, so survival probability of the rat. This is the first question in which the rat and the cat were diametrically opposite in the grid. So the survival probability will start with 1 at time t, usually the survival probability of 1, which is pretty obvious, but as we found out from the from my explanation that as probability survival is inversely proportional to time, so is inversely proportional to time, so we have a decreasing function which will ultimately tend to 0 for a very large amount of time. Okay, so for the second part, is when the rat and the cat are at the same point, at they start from the same point at the center. Here the graph is same as before, but one thing to note is that the probability survival isn't 1 at time t is equal to 0. Okay, this we need to keep in mind, because as we know that they start from the same point, so the probability of survival probability can never be equal to 1. This was the only important thing to note. Other than that, both the graphs have the same formation. Okay, so the second question, which in case of sphere, this can be easily found. We have this same type of graph where even here the survival probability is never 1. Okay, so in any case there isn't such a case in which the rat will survive, because ultimately, like in a very long time, there will come a time when the rat will ultimately meet with cat and the survival probability will tend to 0. Okay, now I have solved the question computationally as well as analytically, and thank you for watching.